presentation which you can also find online. I will try to discuss some of the issues that I raise, and at the end I'll aim to finish at 3:30, and at the end I would be very happy to answer to any question you might have. So the idea of this talk was to essentially go back to March 2004 when HEPEX started and look at what we were doing with the ensembles in meteorology at that time, and look at how the ensemble have progressed. Have they changed? Have they improved? Are more products available now? So I started showing you a forecast for the September 2014, so last year, of flood in Pakistan. As you know, Pakistan has been affected by extreme rain for Pakistan and northwestern India. And 10 years ago, we didn't have what I'm showing you today. On the left, you see a map that with colors, where colors identify the rivers where there is a probability of exceedance of a certain level of discharge. And on the right-hand side, I'm showing you two discharge grams of a discharge at a specific location, Chenab River, Kudai, Pakistan. On the top, you see a 14-day forecast at the 1st of November. You see the distribution of possible levels on the river, generated by driving the European Flood Alert System model using 51 forecast from the ECMWF ensemble. The plot below shows you the same forecast 3 days later. So 2 weeks beforehand, you see that there are some members that clearly identify a probability of exceedance of a red threshold, which indicates flooding. As we get closer to the event, all members start, first of all, to span a smaller range, so being more consistent, an indication that the probability that the range of potential outcomes is more limited, and they all go closer to what was observed. So this is a typical example of something that was not available 10 years ago and is available now. And HEPEX played a role in developing this type of products and developing the science behind it. So as I said, 2004, we have a first HEPEX workshop in March here at ECMWF, where we decided to start this project to demonstrate how to produce reliable engineer quality hydrological ensemble forecasts. Today, if we look around the world, there are several centers, I mentioned here only 2, but there are many more, who produce daily operational ensemble-based probabilistic hydrological forecasts. And progress has been made by sharing knowledge, by exchanging ideas between the meteorological and the hydrological community. So the plan for this talk is to focus on the meteorological ensemble, and I will use actually a lot of ECMWF results to illustrate some of the advances of the past 10 years in ensemble prediction. So first of all, I want to discuss why ensembles are more valuable than single forecast and should be the norm in predictions. Second point would be to review how the ensembles are now used at ECMWF. Third point, to show some performance indices of the ECMWF ensemble. And fourth, to discuss how we are planning to continue to improve the system. So let's move on. Why are ensembles more valuable than single forecast? This is a key question that is asked many times. Why should I use an ensemble system instead of one single forecast? I have to make a decision, I have to decide whether to take action. How can a probability distribution help me? Well, The issue is that a single forecast blue line, after a certain amount of time, start diverging from reality because of errors in the initial state of the system, because of model errors that lead to a divergence later on. As a result, if we had only one single forecast, it would be, well, first of all, at one point we would have errors, and second, it would be impossible to know up to which point can I trust my forecast. The idea of the ensemble is to use an ensemble of them, many forecasts, to estimate the initial uncertainty and then estimate the forecast time, the forecast uncertainty. What does it mean to estimate the forecast uncertainty? Well, it means to be able to estimate what's the probability that a range of events can happen. If on the y-axis you think of a variable like precipitation, users might be interested in looking at what's the mean value predicted, what's the mode, or what's the probability of exceeding certain levels. This is why an ensemble-based forecast is more complete. It gives you the possibility to estimate the most likely scenario and its uncertainty. And in fact, we have demonstrated through the years that ensembles have a higher value. Work done about 15 years ago have shown that if we take a simple decision model, cost-loss decision model, we can then estimate what's the value of taking a decision using an ensemble-based forecast or a single forecast. Here on the left, and you see the so-called potential economic value of an ensemble forecast in blue and of a single ECMWF high-resolution forecast. So on the x-axis, you see a cost-loss ratio. Different users might have different cost-loss ratio. So a user, for example, that could, by spending $20,000, can avoid losses of $100,000, have a cost-loss ratio of 20,000 over 100,000, 0.2. So would be a user sitting here. So such a user, if he used a 6-day forecast of precipitation on a winter period, he would do better. He would have a higher economic return if he took decision based on the ensemble than on the single high-resolution forecast. The same is valid if you look at the dollar variable. Here on the right, I'm showing temperature at 850, temperature anomaly greater than 4 degrees. So the ensemble gives you more information. The ensemble has a high economic value. The ensemble-based forecasts are also less jumpy, more consistent. Forecast issued one day after the other, so at different times, valid for the same verification time, are more consistent if they're based on an ensemble forecast. Here what you can see from a work by Erwin Soter et al., published in 2009, is the inconsistency index of the ECMWF and the UK Met Office single control forecast and perturbed forecast and the ensemble mean. As you can see, at the early forecast ranges, there is not a big difference between the inconsistency of the ensemble and single control forecast, which at the initial time is centered more or less on the mean of the ensemble, exactly on the mean for the ECMWF system. But as you moved into longer lead times, a forecast based on the ensemble mean is much more consistent than a forecast based on a single control. So users that use an ensemble mean forecast see a more consistency between forecasts issued at at consecutive days. Please note that given that the ensemble mean is a smoother forecast and less variability, to generate this curve, one needs to take that into account. And in fact, these curves have been generated by normalizing the error, which in some way this inconsistency is defined as the distance between the two ensemble mean normalized by the variability of the ensemble mean. And for the control forecast, it's the distance between two consecutive control forecasts normalized by the variability. So this is taken into account. So ensemble-based forecasts are more consistent and more variable, give more information, and allow to estimate the probability of exceedance of any type of variable. So not all users are interested in what's the most likely scenario. Not all users are interested in what's an average is going to take. Some users might be interested simply in assessing the probability that some extreme values happen. Because if these extreme events or rare events happen, they might incur huge losses. Well, if you have a whole PDF, an ensemble-based estimated PDF, you can estimate such a probability. This would be impossible with a single forecast only. I mean, it's not actually impossible in the sense that one could think of tracing a single forecast using a statistical Gaussian in some way, but in that way one would lose the flow dependency, which, as you will see later, is very important. So let's move to a second point. How are the ensembles used now at ECMWF? So this is how we were running our system, our operational suites in 2004. We had, is everything okay, Frederick? Yeah, okay. So we had a high-resolution analysis that was giving us the unperturbed central state of the ensemble, and then we were running 51-member ensemble up to 10 days. We had seasonal system 2 that was producing 31 forecasts up to a seasonal timescales and one single high-res model. We were using ECMWF reanalysis to generate the initial condition for the past cases. Today, we have an ensemble of data simulation with 25 members, which help us also identifying analysis uncertainty together with 4DVAR. EDA also provides flow-dependent estimates of a background error statistic to 4DVAR. We have an ensemble of ocean analysis to initialize the ensemble, the medium range monthly ensemble, which is now coupled to an ocean model from day 0. The ensemble runs up to 32 days instead of only 15 days. Seasonal forecasts are based on 51 members now at high resolution. Not only that, we have introduced and improved the way we simulate observation and model uncertainties. What do we do with the ensemble? Well, we generate more and more products where, for example, we show ensemble mean forecast, most likely scenario, with a measure of the dispersion of the ensemble given by the standard deviation. Here are two examples of that. We use the ensemble distribution to estimate, to identify areas where some extreme events can happen. This is an example of a forecast of a product called Extreme Forecast Index that identify regions where extreme precipitation, extreme wind in this case, can occur. This was a forecast from the 4th of September at 12 UTC, valid for Sunday, last Sunday, the 28th. And one can use this type of map to identify regions where something extreme could occur. By clicking on the point, one can bring up and see it, the whole distribution of the ensemble members at that specific location. In this case, I said there was extreme precipitation, so precipitation increasing between the 26th and the 28th. Wind speed is increasing. And in fact, if one looks at the distribution, the cumulative distribution function for wind and precipitation, they are shifted to the right compared to the climatological distribution, to the model climatological distribution. So the fact that the forecast distribution, red for the most recent one, in blue the one issued 12 hours before, 24 hours before, and so on, the distance between these two give us an indication of how extreme is the event that we're going to observe. Okay, and here you see a blow-up of a 24-hour precipitation CDF and the CDF for maximum wind gust. By computing the area under these two curves, the climatological, model climatological one and the forecast, we can compute an index, and the index is greater than 0.5, identify regions where something extreme might happen. I said that we are now running also an ensemble data assimilation system. Well, in that respect, ensembles are used to estimate what's the most likely, what's the uncertainty, the forecast, the uncertainty in the first guess. So depending on the flow, certain regions might be more, the first guess of a background forecast, which is merged to observation to generate analysis, might be more in error than in other regions. So the ensemble of data simulation provides us with this information so that we can give more or less weight to the observations in areas where the background is estimated to be more in error. We give more weight to the observation, while in areas where the EDA says that the background error is small, we can give more weight to the background. And as you can see from this plot, this matters a lot. This is the horizontal correlations at one grid point. This is the weight that, so this is the correlation length in summer and in winter, in red for one place, for two different points. One is 45 north and one is 45 south on the Greenwich meridian. So you can see that the statistics are not the same. They change with the time of the year. They change with the location of the point. This flow dependency in the estimation of the weights to give to the background is essential to be able to make a better use of the observation that we collect daily. So we look at why ensembles are more valuable than single forecast. We look at how ensembles are now used at ECMWF, and I want to show you a few plots of how our medium range and monthly and seasonal timescale forecast perform. I might skip some of the slides, but you will have access to them from the web. So this is the systems that we are running today at ECMWF. I mentioned the ensemble of data simulation, which provide analysis and uncertainty of a high resolution for DVAR. We run a high resolution forecast up to 10 days, coupled to a wave model. We run a 51-member ensemble up to 32 days, twice a week, twice a day up to 15 days, coupled to the ocean model from day 0, and we run a seasonal forecast once a month with 51 members up to 7 months, 13 months every quarter. So how do they perform? Well, first, the property which is essential that ensembles have is that they are reliable. Reliability, what does reliability mean? Well, it means that on average, you would expect that the average error of the ensemble mean is similar, is actually, is very close to the average spread of the ensemble. In a reliable ensemble, when the ensemble spread is small, you would expect to have the analysis within the distribution spanned by the ensemble member. So if the spread is small, the distance between the ensemble mean and the ball of the ensemble should be small, and so you would expect a small error. While when the when the spread is large, you cannot say really much about how the error of ensemble mean could be. It could be small, but could also be large. So it's important to check that ensemble spread, in this case measured by the ensemble standard deviation, and the error of the ensemble mean match each other. How is it in our system? Well, this is the statistics of the time evolution of the error of the ensemble mean in solid and the standard deviation of the ensemble for geopotential height at 500 last summer, June, July, August. Very good match up to day 7 or 8, and then an under dispersion of around 5%, as you can see under here. Here you see also the spread under or over dispersion during the past 4 years. If we look at winter, the match between the two is much closer. So this is last winter, DJF, so we should expect the ensemble next winter, this winter, to behave actually very well. Why does the ensemble perform better in winter than in summer? Why is it more reliable in winter than in summer? Well, it's because of a methodology we use to estimate the initial uncertainty. It works much better during the winter seasons when baroclinic instability is the key source of, say, perturbation growth and so forecast error growth, while in summer where small scale, moist processes, convection driven are essential, our perturbation strategy work a little bit less accurately, and this is why the system performs very well in winter but not so well in summer. If we look at other variables, again, another way to look at the reliability is to compare the probability, forecast probability, and the observed frequency of an event. This is again for October, November, December 2012, the last season I could find in our verification database. You see how the ensemble observed probability match the, forecast probability match the observed frequency for precipitation 24-hour accumulated greater than 5 millimeter at 6 days verified against observations over Europe. We want to be on the diagonal. We are not far from the diagonal, but so obviously 6-day forecast, it's good, it's not perfect. If we look at another variable like the temperature, again, this is a temperature anomaly greater than 4 degrees, a 6-day forecast verified against analysis over Europe. The match is closer, so the system is more reliable. So this already indicates that for precipitation, there are some, it's more difficult to make reliable forecasts. And another way to measure, so we talk about reliability, let's now talk about accuracy of the probabilistic forecast. So one way to measure accuracy of probabilistic forecast is by using this score, which is called the continuous run probability scale score. What does it do? It measures the distance between the forecast PDF, in this case for precipitation, and the observed PDF. Clearly, the observed PDF is a delta function because at one point, if it rains 25 millimeter and we are considering the event precipitation greater than 20 millimeter, the event occurs at one grid point, so the value is 1. While for the forecast, we might have a probability of, I don't know, 80% or so. So by computing, one can compute the distance between these two distributions, compute the continuous run probability score, and then we compute the score for climatological forecast. This is our reference, and the skill score is defined as the score of the forecast versus the skill of the climatological forecast. So positive values means that the ensemble is more skillful than the system. So what you see is that for this ECMWF ensemble, CRPSS in June, July, August, which is the most difficult season, is above 0 up to 6.5 days. So we can issue skillful, accurate, and reliable probabilistic forecast up to, say, 6 to 7 days in the summer. The ensemble, I said, runs up to 32 days. How does it perform if we go on the longer time scale? Clearly, over the longer time scale, we cannot pretend to predict accurately precipitation at a single location, but we are able to predict in a skillful way large-scale patterns. For example, organized convection in the tropics, as indicated by the MJO, the Madden-Julian oscillation. What you see here is the score of the forecast with our last version, which has been implemented with coupling from day 0. versus the version before. So we correlation coefficient between our forecast of the MJO and the observation is above 0.5 up to about 32 days. If we take the 0.6 line as a threshold, we cross it at around 28 days. This slide is simply to show you that we are not the only one issuing monthly forecasts, but we are definitely the one issuing best, most skillful forecast for this type of organized convection. The MJO always comes from a comparison paper published 2 years ago. Now I'll skip some slides, otherwise I don't manage to finish on time. So this slide simply shows you some extreme events. The point I want to make is that even if predicting daily accumulated precipitation is very difficult, if we accumulate over a week, we have clearly more skillful signal. We can extract a signal from our ensemble. And this is particularly true if we look at some extreme phenomena which are triggered by large-scale circulation patterns. I'm showing here 3 examples of flooding over Pakistan. On top, you see the observed weekly average anomaly of precipitation. And then you see a week 1 forecast, day 5 to 11 from our ensemble system, day 12 to 18, 18 to 20, 19 to 25, and 26 to 32. So essentially it's a week 1, week 2, week 3, week 4 forecast for this weekly anomaly. And this was the flooding of 2011, where we can see a signal already 4 weeks before the event. 2012, similar story. We lose the signal after week 3, but you can see that week 1, week 2, up to 18 days before the event, we can clearly see that something anomalous was going to happen. What I'm showing in this, what each of these panels shows is the anomaly of a forecast with respect to the model climatology, and it's colored only when the forecast PDF is statistically significantly different from the climatological PDF. 2014, again, 1-2 weeks before the event, we have a signal. We don't have any signal at week 3 and neither week 4. I mentioned that we are running, so we talked a bit about the ensemble of data simulation, how it's used to estimate the uncertainty in the analysis. I talked about the medium range monthly ensemble, how this can be used to predict the weather up to 10-15 days and over a longer range. We are also running a seasonal ensemble, which is used to predict large-scale pattern up to 7 months every month and 13 months every quarter. How successful are we in this? Well, we are very successful in predicting some phenomena, especially over the tropics. For example, El Niño. Here you see 4 consecutive 1-year forecast of El Niño. In dotted, you see the observed SST average over a region in the middle of the Pacific, and the 15 seasonal forecast members, forecast from November 12, valid up to November 13, forecast issued last year for this November. And as you can see, it's pretty impressive how well the system is able to capture transition from La Nina condition to El Nino, more neutral type of condition, and again going towards El Nino warm condition this year. But seasonal forecast, how seasonal forecast over Europe or say the extratropics? Well, this is a very challenging area where to make skillful seasonal prediction, especially if we look at precipitation anomaly or droughts. But there are again cases where we start seeing good forecast being issued. This is a case of summer 2012. I'm showing here the an observed index that it's usually used to predict droughts. So here is what was observed according to ERA interim, our reanalysis over 3 months, May, June, July 2012. This is our forecast 4 to 6 months before the event, issued the 1st of February, and this is our forecast issued the 1st of May. As you can see, there is a good indication on the 1st of May that there is going to be drought over Eastern Europe, as was observed. In general, reliability of seasonal forecasts for temperature are not too bad, but if I showed you reliability diagrams for precipitation, as you can see, the diagram is pretty flat. So there is still a lot to do to try to improve the prediction of precipitation. This is the forecast over Europe, this is the forecast over North America. So to conclude now, how are we planning to further increase the ensemble performance? Well, the challenges and the opportunities lies essentially in trying to design systems that are able to simulate all the scales which are important, include the relevant process, and initialize the forecast in an accurate way. I'm going now to skip the slides and just want to mention the areas in which we are working. Clearly, the problem has to be addressed in probabilistic terms, so we need to think ensembles and think probabilities. We need to try to increase the resolution of a system because we need to resolve phenomena and scales to be able to extend the length of the forecast. As I said, we need to improve the model. We need to have better estimates of the model climatology so that we can calibrate our current forecast. As forecasts improve, the plan is to extend the forecast length of our forecast. I'm going to skip this slide because it's time to finish, and I just go to the end of the talk, and you're welcome to ask me questions about the remaining slides. So as I said, opportunities rely on building better coupled models. We are in this situation today where, for example, if we look at the marine aspect, we have an ocean wave coupled to the atmosphere. There is a weak coupling with the ocean dynamics, and the ocean dynamics is also coupled to the atmosphere. There is no sea ice, for example. In the land surface, there is no closure of the water balance. In the atmosphere, we're still missing all the chemical aspect. The future is based on building better Earth system models that can take into account and simulate all relevant processes, relevant in the sense that they matter to improve the prediction of weather up to, say, a month ahead or a season ahead, which is what we're doing here at ECMWF. So what you will see is the addition of chemistry modules, cryosphere, better coupling of the ocean system, closure of water cycle. This will lead us to better, more skillful forecast. Secondly, we need to move from this rather not very integrated approach to simulate initial and forecast uncertainty to a more coupled way of thinking and approaching a problem, where we can generate coupled analysis of our system from which we can generate coupled forecasts using the same type of model. So this is how I think we will be able to further improve and provide even better forecasts for the future. Thank you very much for listening to me, and I'm happy to answer questions if you have any. Frederick, to you.
Thank you very much, Roberto, for a very interesting talk on covering a lot of topics. And I'll now leave the floor open for any questions. If you have questions, you can unmute yourself and ask them directly to Roberto.
Question, can you hear me?
Yeah.
Maria Elena speaking.
Hi.
Yeah, okay. Hi, Roberto. I like very much your talk. Thank you very much. I like when we talk about hydrometeorological ensemble forecasting, and we also talk a lot about precipitation, temperature, and a bit less about discharge, of course, because we probably started a bit later in hydrology. But I'd like to know your feeling about how these two communities, meteorology and hydrology, are working together now, when they started taking from each other insights or challenges and starting to working together. And how do you see the future on these two communities working together?
Well, I can give you the example of what's happening here at ECMWF. When we started 10 years ago, we started having one hydrologist and 2 or 3 working essentially to use weather forecast to drive hydrological models. This is still the case now. The European Flood Awareness System that we run here for JRC is essentially using weather forecast to drive the river, the discharge model. But we are working to try to include this, the river routing and so close water bubble in our atmospheric model, because it's clear that especially if we want to make good seasonal forecast, there are areas of the world where it's essential to have the right freshwater flow into the oceans. So what I can see happening is that hydrologists will help, will actually build with meteorologists more complete models that can be used to extend and make possible the prediction at longer time ranges. This is one area. The second area is clearly in trying to share knowledge and information. I mean, in hydrology, my understanding is that there is a lot of expertise in calibrating and in thinking of in a stochastic way of a forecasting problem. This, as we do in meteorology, but maybe we are doing it in a slightly different way because our models are more complex and we cannot really run many simulations. So this is another area where we can learn from each other and exchange tools and ideas.
Thank you.
Do you have any further questions? You can also send them through the chat function if you don't have a microphone.
Can I ask another one, so?
Yeah, go.
Okay, I'll take the opportunity. I liked also when you're talking about the checking reliability. In a reliable ensemble, we have the spread that should be close to the error of the ensemble mean, if I understood well.
Yeah.
Can we also say that we can also have all this inferior than the standard deviation of observations, of historic observations, to achieve also some accuracy?
Sorry, I didn't capture all what you were saying. Can you say again?
Yes. I was wondering that in this small equation that you said about spread should be close to error in a reliable ensemble. So spread of the ensembles close to the error of the ensemble mean. Can we add a third part on this equation, on the right side of this equation, that this spread and error should be lower, much lower than the standard deviation of the observations, so we can have also some accuracy, reliability, but also some more accuracy than just climatology?
Sure, sure. I mean, one should actually ideally take into account observation uncertainty as well when this is computed. Yeah, yeah, definitely. You're very right. And this is in fact something that we do. What we see when we do that is that while so in the early forecast range, observation uncertainty, so analysis uncertainty matters in the sense that it's more or less the same size as the forecast error. When you move into lead time, say beyond 3 days, the error is much larger than observation uncertainty. You can see the observation uncertainty is more or less the same amplitude as the spread of the ensemble. I mean, this is clearly very valid in our case for geopotential at 500 or temperature at 850, but I think we are underestimating in terms of precipitation. But for this variable, you can clearly see that this is very important if you want to verify system in the short range. But when you move in the longer lead time, taking observation uncertainty into consideration would not change the results dramatically. But it's a big issue when you start developing and you want to develop and tune this ensemble of data assimilation. It's a big issue when you want to verify whether your ensemble of analysis gives you the right level of uncertainty, because here you're working over a very short period, say 6-12 hour forecast range, and at that time forecast errors are roughly the same amplitude as observation uncertainty. So one has to take observation uncertainty into account to have a proper diagnosis of how the ensemble of analysis or how your analysis uncertainty is compared to what should be. So that's very, very important. Less important, as I say, as you move into longer lead times. Going back to your first question about how the two communities can interact, I think that one of the successes, maybe the biggest success of HEPEX, for example, is that we really managed for 10 years now to bring together these groups of scientists working with two communities to discuss issues which are relevant for both, and to try to build systems together, try to talk the same language so that we can exchange information. I think this is very important. I mean, at the beginning when I was co-chair, I was thinking, wow, is this all? Can we aim for something more? Is this really important that we managed to run a very successful workshop and we have people engaging and discussing? Actually, if I look back, I think it is a very important aspect, because if I look at other communities, for example, climate and weather scientists, I wonder whether they talk and exchange information the same level or not. It's essential that this happen. I think, for example, the project like HEPEX has been very successful in doing this, spontaneously generating this exchange of information, because clearly everybody was gaining by sharing information, because everybody was gaining extra information together, we could move forward. So I wonder whether anyone else has questions. Otherwise, Frederick, what do you want to do?
Yes, we can ask if anybody else has any more questions. Otherwise, you can always ask Roberto through the on the HEPEX blog. Send questions as well, and also the talk will be uploaded on YouTube after this, and also the slides will be available. So do we have any further questions? Okay, if not, then I thank Roberto and everybody else for listening to this webinar, and we will be back in beginning of November with a number of talks from the HEPEX, joint HEPEX HSAP workshop here at ECMWF. So you're welcome to join those talks in beginning of November, 5th to 7th of November. Okay, thank you again, Roberto.
Thank you, Frederick. Thank you, everyone. See you all soon, hopefully. Bye.
Bye-bye.